Okay. Okay, let's go through this. Okay. So today I will be going over how to apply deep learning to predict stock prices. Okay, so there's some steps we need. Oops. I just ate a Szechuan peppercorn for no reason, and it's burning my mouth. Okay, so today we will be using stock price historical stock price data in order to try to predict future stock prices using deep learning. So some deep learning has been applied to a lot of things. Like one of the most well-known applications of deep learning is one of the most well-known applications of deep learning is for image recognition, and they typically use convolutional neural networks. So what that means is that they apply a convolutional layer. They sort of blur. So they sort of extract some features by like blurring certain parts of the image. So let's see. Oh, shoot, I should have. Okay, so you can see here. You can see here that like this is the different part. This is the image with different types of blurs, and you can sort of see it extracts some features. Here it sort of gets like the front of the car. This sort of gets like the frame. This gets like the just everything like, and then there's some blurring layers. And so what that does is it helps the deep learning model to try to like find layers, because like if you think about it, an image has a bunch of pixels, so trying to match them up like one-to-one with like you have a like to another car, that's one way to just tell if it's a car. You can match all these pixels to another car, but that'd be like, what happens if like usually a lot of pixels might be off. So what you do is you can blur it, because the more you blur it, when you blur two images of like a cars, then they sort of look more similar. And so we can sort of do the same thing with stock prices. We can sort of take open, high, low, closed volume data and sort of blur it to try to detect patterns and use these patterns to try to predict future prices. Okay, so our first step in the process is that we will need to get data. So as you can see here, there's an object called QuantBook. This is an object provided by QuantConnect that allows us to do a lot of cool things, like namely get data. So first we need to add what a security that we want to subscribe to the QuantBook, because the reason they have this is so that we don't subscribe. It's easier to listen into the data of subscribe to the data of just a few securities, because like if we didn't have, if we just wanted like if we wanted crypto data, which coins does it track? There's a lot of coins to track. So what we can do instead is choose a coin, specific coins, and we can even add Bitcoin if we wanted to. Crypto. So this helps the QuantConnect narrow down on which coins that we want, and that makes like data requests a lot easier, because it doesn't request all the crypto data. It just requests the few that we actually want. Okay, so And then there's a thing called history, and this just basically gets the data of the coins the data of the securities we are subscribed to. We subscribe to ETH here, and it gets the history of that at a security. So let's just look at what this history looks like real quick. So it uses a multi-index. So the first index is based on the symbol of the security, and these symbols, and we use a symbol instead of a ticker because often there's more information. There's more information in sorry. There's more information in a whole symbol than in just a ticker, because often it also includes the exchange data. Like say you have Apple, it will also say what exchange it is on. And I'm pretty sure Apple's on NASDAQ, for example. So AEPL doesn't really tell us much. You see here, AEPL. But with the symbol objects, Quant Connect has these symbol objects that have like a bunch of like letters like AX, blah, 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 that also give a lot of information on this ticker. It's like more detailed ticker. It's like a ticker, but with more details. And we can actually get the ticker, like well, it's not really ticker, but. So we can see here, this is less detailed, or we can do, you can see here what we saw earlier. So this is ETH USD, but then as ETH USD XJ, and that gives like exchange data. And with like something like Apple, it also have like extra information on the exchange. Okay, so you can see here is a multi-index. However, we do not want a multi-index. We only want the data for ETH. Like normally we'd have like more stuff like BTC. Say we have like, we also have a request for data for BTC, and this would have another index. So we just want the OHLC. So this is not in the format we want. So what we can do is do loc, and loc is just basically data frame indexing. Let's look at this DF. And now this is our ETH data with only one index, and this will be a lot easier to work with. Okay, so we have our data prepped. I mean, we've gotten our data. Here, let me just do DF ahead. There. Okay, our next step is to define some constants that we will be using, and like global stuff that we will need. Okay, so we can see here, there's a bunch of variables here. However, we only want to use the open, high, low, close, and the volume. So what I've done here is just have these input bars here. Oops. And what we can do is just index it. So you can see here, there's a bunch of variables here. But if I do that, I only get the open, high, low, close volume here. So we will be using this later. Actually, we could just do it right now. Let's just do it. None. Okay, so I've also defined a number of time steps, and this is to determine how many time steps we want to use to predict into the future. So we use 15 time steps. That means we use the past, so say we use the past 15 days of data to try to predict the future prices. And the scalar, so often in machine learning, we need to scale our variables. Well, it's good practice to scale your variables, because say you have like, because like in the real world, variables usually like have different ranges, right? So say So we don't want the variables that have a super large average to like dominate the neural network. So say we have a bus and we want to determine how fast it is, and we use a machine learning model. So one thing we could use is the grams of the bus, like how much the bus weighs in grams. And another variable could be the number of students within that bus. However, because the bus weighs like hundreds of thousands of grams, that variable, the weight variable, might overpower it. So what we do is we have to normalize it, and so we scale it down to like a range within like 0 to 1, or in this case, standard scalar. We scale all the data to a normal distribution. Then we also have this is like a sort of like an enum. We will use this to label. So our deep learning model is a classification model. What we are going to do is try to predict the direction of the stock price movement. So up is if the stock price goes down, up, down is if the stock price goes down, and stationary is if the stock price just stays flat. Well, not stock price. Well, you get the point. Well, if the price is the security. Well, we're using Bitcoin. Okay, so now we will define a function. So if you have any questions, just please ask me. Let me open the chat. Okay, so I've defined a function here called prep data. What this does is it prepares data for our machine learning model. Often in real world, like data won't be always in format to be fed into machine learning model because sometimes you have a matrix. No, you have like a big spreadsheet of data, but you want to use 5 rows for one prediction. However, if there's like 21 rows, how do you do that? And that is the point of this function. Okay, so I have some variables here. So rolling average window size. So what we want to do, instead of predicting the next bar of data or the closing price of the next day, instead what we do is we try to predict the movement of the prices of the average of the next 5 days. The reason we do that is because it's probably easier to estimate what the average will do because there's more it's like averaged out. Actually, and I also took this network architecture from, I just stole it from a paper. Well, not really stole it. It's from a paper, so it's from an ArcSiv paper. Yeah, I can post it in the chat. All right, I'll just find it later. Okay, so here we filtered out only the variables we want, as I explained before, like the input bars. And this is the open, high, low, close, and volume. And we also need to shift our data because when we do the moving average, okay, so let me draw this out. So say we're using two moving average. So so these are all like bars of data, like OHLC within each bar. And we want to use the past 5 data to predict the average. Average. So what we need to do is we take the average value, and when we do, okay, so when we do rolling average using pandas, this point will be the average of this. However, I want to shift this average value of these three variables over here. So like, say these are O, H, L, C, V. And then this will be a new column. This will be AVG close. So I want to move this average over here because it'll make the processing of the data easier because we want to, so like we're here and we want to, so we have data up to here and we want to predict the average over here. So when we process the data, what we can do is we can take these 5 variables and stick it into a list and take this and also stick it into a list. We're not going to take this numeric value exactly. We're going to actually label this with up, down, or no movement, letter. Okay, so that's why we have a shift. Okay, so the first thing we do, as I mentioned earlier, we're going to find the moving average, and that sort of like simulates the mean because rolling average, mean and average are the same thing. So since we are trying to predict the average of the next 5 time steps here, so we've decided the average window size to be 5 as a keyword argument. So our window is equal to this. Then we take the mean, and we have to shift it back because this is the mean. This is the mean we're trying to predict, and we have to shift it back here. Okay, hopefully that makes sense. If it doesn't make sense, I could try to explain it later. Okay, so however, what we want to do is calculate the change of the close values, the percent change. Okay, so this has OHLCV, open, high, low, close values. So we want to take this close, and since we calculate the average of the close and shift it back, we want to divide this value by this close value to see the percent change in the average close value from the last close value. And this is what this is for. This is what this is for. And then we take these percent changes and we label it using this function here. So our stationary threshold is a variable that determines whether or not a movement in the stock price will be classified stationary or not. I didn't put stationary. I made some changes to this code, so I sort of disappeared. Okay, so if it only moves 1% of 1%, we'll classify it as not moving. So say if it's like $10,000, then you divide by 100, then it's like 1%, 1%. So if it moves, so say if the stock price is $10,000 and moves $0.50, then we consider the stock movement. Then we consider the stock to not have moved, and therefore the price was stationary. And that's what the stationary is. Okay, so this is how we apply the labels. Okay, after that, and the reason we have x is equal to 1 is because this does it row-wise. We don't want it to do column-wise because that doesn't make sense, right? Because we're applying to this, and this is one column. We don't want to apply this operation to all columns. We want to apply it to every value in this column, and so that's why we go row by row. Okay, next I define 2 lists to hold the input data and the labels. And so these are the labels, the movement labels. And so what I do is I iterate through the data frame. Okay, so if you remember earlier, NT steps is the number of time steps we want to get. Wait, no, this is label. Sorry. Oh, this is actually wrong. Wait, no. Sorry, I was doing something else. On a different model, I'm curious. Just kidding. Okay, this is fine. Okay, so what this does is it basically finds. Okay, so if you remember earlier, we like labeled it with like 3 directions. The reason we have to use numbers, like we label it with numbers, is because machine learning models only work with numbers. So if you put like the string up into it, it wouldn't be able to work with it. That's why. So what we can do is we can actually like translate this back into something that we can understand. Like say if that model outputs 2 as its prediction, then we can convert this 2 into stationary, and then we know the stock price that we will predict the stock price won't move. Okay, so this is a 0 to 2 label, where 0 is where the stock price will go up, etc. Okay. And then what this does is it pulls so input vars, if you remember earlier, input vars is the variables we want to use to predict the future stock price, the open, high, low, close volume. And so what we do is we take the ith to the ith plus nt steps. And so what that will do is give 15 rows of data. And what we could, and using it with this, we keep doing this like then I plus 1 until we get to like near the end, where like, because we near the end. And the reason we have to have like this minus stuff is that because like say we're at the last index, like the last index, then we do I to I plus nt steps. We'll go past that, and then we'll have like a out of bounds exception, like an array out of bounds. Okay, so then we convert these lists of NumPy arrays. Oh yeah, the dot values basically takes the values in the data frame and converts it into the NumPy array. And so what we did here is we've converted the list of NumPy values. The list of NumPy values into one big NumPy array. This is what this does. And then here we record the shape of the this new giant NumPy array. We reshape it, and then we apply the scalar. If you remember before, the reason we do scaling is so that certain variables don't have like a much larger impact on the prediction just because of the magnitude of that variable. Like remember the kids and the grams of the bus, like because the grams is such much larger magnitude, it might like overpower the model, even though like the number of kids in bus should also affect how fast the bus can go because of the downward force. Because the kids they have mass, they apply downward force, and thus there's more friction, and then that slows down the bus. Okay, data. Okay, and then so however, because sklearn usually doesn't work with 3-dimensional data, we like reshape it to a 2-dimensional array here. So So earlier there's 3 dimensions. That's why the shape has like 3. It's the tuple of the shape is of size 3. What we do is we just basically just sort of like merge the first and second dimensions. And this is now 2D. We apply the transformation and then we make it back into 3D. And something about, this is special for Keras. Usually in sklearn, like you can just use 0, 1, 2 as the labels. However, utils.category, the reason you need to do that is because Keras just wants it like that. It's easier for the neuron. I think it's easier for the neurons to interpret that. Okay, so let's see, let's say our labels equal 1, 1, 2, 1, 1, 2, 0. And so let's see what this does. Utils dot. You can see here, so it, like usually you want to start at 0. So what it does is it puts 1 at the index. And this is sort of like dummy. This is sort of like, if you're familiar with dummy variables, this is what's sort of like. So you can see here, so this is the first index, this is the second index, and this is the 0th index. And this is much easier to working with neurons because we have 3 classifications, our final categorical classification will also have 3 neurons. So what it does is it just points to one of these points to all 3 neurons with like a probability, and we can, yeah. Okay, so sometimes you might not get one of these labels. So say if the price of ETH just always goes up and it goes sideways, but never goes down. That's usually not the case. It usually goes up and down and sideways. However, sometimes that might not happen. So just to be safe, we put the num classes here just to make sure that it'll give us the right shape. So say we know that our labels can be 1, 2, 0, 1, 2. However, if we do not have any 2s in there, it will be the wrong shape. And if we have 3 output neurons, but each neuron, so each output neuron wants to point to one of these. However, there's nothing here for the 3rd neuron to point to. So what we can do is num classes equal 3, just to make sure that we get the right shape. And you can see here, it's just all 0s. And that is because we never encounter a 2. Okay, next we want to build our model. So let me just show you guys what this model looks like. Okay, so first we have the input layer. This is where the data is fed through initially. Then we extract the features with the convolutional layers. Like with image recognition, you like try to extract the edges, like you extract like the circles and stuff like that. And we're basically doing the same thing with stock prices and try to extract features from the open, high, low close data to see if these features can help us predict future prices. So we take this layer and we sort of split it into 3 layers. And this is because we want to add a temporal element, because like say the past 3 bars of data, the past 3 data of OHLC has more say or less say in predicting the future. So what we do is since we are using 15 time steps, the long term is the first 5 steps in the time series. The midterm is the middle 5 steps, and the short term is the most recent 5 steps. And so what this does is it adds it tries to add an element of time. And then after that, we apply another convolutional layer to them. Then we combine these 3 layers, and then because our input data is like a 2D, like for each output, it's like a 2D array because we use 15 time steps of OHLC data. It's like a 15 by 5. Okay, so yeah, it's like a 15 by 5. If you know pandas, it should be like it should make sense. Like it's like a 15 by 5 matrix. And so when we flatten it, it just turns it into like a 45 by 1 matrix. And then that's easier to create an output. Don't okay. So as you oops, wrong. Let me close this. Okay, as you can see, we split the layers into 3. We split 1 layer into 3. And usually we use sequential models. With a sequential model, you have 1 layer here, 1 layer. So you want to have these side layers. You just have this layer, 1 layer, 1 layer, layer, 1 layer after another. And there's no splitting. So we cannot use a sequential Keras model. We actually have to use a functional model. So, no, this only really matters if you know Keras. Okay, so here we start with the input variables. And so we have like the number of time steps times the number of inputs. That's our shape. And since this is 15 as you remember. And this, we use 5 input variables, OHLCV. And so this should be 5. Then we extract the data. We feed it through, we activate it with the ReLU. We split this convolutional layer here, right? So we split it. We split it into 3. We get the first part. Split it into 3 again. We get the first part. 0th part, the first part, and second. And this is like this is the Lambda layer. What it basically does is it takes Lambda layer. You create a function to create the layer. So Lambda x is a Lambda x. So in Python, lambdas are 1-line functions. And then after that, we pass in the previous layer we want this to be connected to. So you can see here. So inputs, we define inputs. We create a conv1d layer. Then we pass in our inputs. So this layer is connected to the feature extraction. We take this feature extraction and connect to these 3 layers, and so on and so forth. And you can see here, this is this. So if you use the wrong layer, or say you introduced a random layer, or say long term. So term wrong one, wrong, like here. Okay, dance. And so you've created some random layer, and then you do this. This would be no longer connected. These two wouldn't be connected. So you want to make sure that you keep passing the previous layer as an argument to the next layer. Okay. And so we take this, after we pass in each of those layers through our own convolution layer, we concatenate these 3 layers, and then we flatten it. And then you see here, this is important. We need to use 3 here because that means, because we are trying to classify it into 3 classes: up, down, and stationary for the movement of stock price. So if we use 2 here, then we wouldn't have enough output neurons. Okay, after that, we want to so we want to specify to the model what layers that we want to use. So inputs, we've defined the input layer, outputs, and this is our output layer. And because we kept passing in the previous layer to the next layer over and over, that's how it knows to keep passing it through from the inputs to the feature extraction to these three terms, these three split layers. That's how it knows to keep passing it through. And then it stops at the output layer. And then we have to compile this model with some, and we add some more data. The optimizer is Atom. There are different types of optimizers that are LBFGS. That stands for like something. It's like super long. Yeah, you see that right there? Do you see that? It's long name. Okay, and so what the optimizer does is it sort of like, different optimizers are good for different data sets, like LBFGS. All you really need to know is that it's good for small data sets. Atom is good for like moderate data sets, and SGD or stochastic gradient descent is like really good for large data sets that you want to continually train with new data. Okay, a loss is categorical cross entropy. So usually, like when you're doing a regression problem, you want to, like, say you're doing linear regression, you want to minimize the R squared, because when you minimize the R squared, that means the line has like low error to each of the individual points. However, we are not doing a regression problem, so we want to minimize the categorical cross entropy, which is like the R squared equivalent, very similar to the R squared for categorical classification. From logits means that you want them to range, you want the values to range from 0 to 1. Well, that's what I'm pretty sure. To be honest, I'm not 100% sure, but I'm pretty sure that's it. And then we return this model because we've put it inside a function. And we don't need to put like build, we don't need this build model function. We can just like shift tab this all back. We don't need a prep data function. We can shift tab all this back and just run once. However, I put them in functions because it's easier to reuse these functions. It's also easier to like paste it into when you want to use it within like a trading algorithm. Okay, so here we prep the data. Okay, let's just look at what this data looks like. So just a bunch of numbers. Okay, I think so. Let's look at what this labels look like. Labels one. You can see here. Okay. Okay, so here we build our model from this function. And then we fit the data and the labels here. Something nice about Keras is that it allows you to automatically split the data for validation testing. In sklearn, what you'd have to do is import a train test split function, and then you have to split the data, then you have to fit the model to the training data, and then you have to use the testing data to try to predict it, and that just adds a bunch of lines of code. However, one thing nice about Keras is that you can just automatically specify the train test split and do all the training and whatnot in one line by adding a keyword argument called validation split. And what this does is it takes 20.2 or 20% of all the data and reserves that for testing your model, because you don't want to train. The reason we do this is because you don't want to try to predict on data the model has already seen. right? Because it already seen that data, so it might predict it overly well. And it will also help us determine if the model is overfitted. It just fits to the noise in the data. And if it fits too well to the random noise within the data, it might predict for new data if never seen before really poorly. And epochs basically tells us how many times do we want to retrain our model with the data. You can see here it keeps running epochs, and like the more epochs you have, the better your model will fit the data, but at the same time it might overfit. So you have to be aware about that. Okay, so let's do prediction. For the sake of making this easy, I will be taking data that it potentially has seen before. However, I'm just trying to show what the output of a model looks like. So let's look at data 0, data 1, 0. As you can see here, the 2 square brackets at the front, we know this is a 2-dimensional data 1 of 0. The first input is 2-dimensional. However, since Keras often works with tensors, it wants its input to be 3 dimensions. And this is because usually we give like multiple data to predict. However, we only want to predict for 1 input. So that's why we have to add a new axis. And let's just see what this output looks like for now. You can see here, it is a 2-dimensional array with 1 array within the second dimension. Well, I don't know. It's kind of confusing. So like you can see there's double square brackets, yet there's only like one 1D array within this 2D array. So what we can do is we can get the 0th element of the output. And it should basically look the same, but it has a 1 less square bracket, which reduces dimension. Okay, let's just do output equals output 0. Then we want to know what directions. Okay, so this since this is in the 0th index, and if you remember from before, direction dot up is 0, so 0 is up. This means that the model predicts that there is a 76% chance that the stock price will go up, and a 10% that it'll stay flat, and a 13% chance that it will go down. So how do we turn this into a single classification? So what we do is we get the index of the max value, and NumPy provides a very useful function called Rmax, and that gives us the index of the maximum value. Because there is the highest probability for the stock price to go up, we want to decide our classification. We want to predict the stock price will go up. So let's try this out. Direction equals argmax. And let's just show this direction. And we can get 0, and since 0 corresponds to up. However, how do we get the confidence? To get the confidence, since this was at the 0th index, and we get it 3 probabilities, what we can do is use this index to put it back into the output and get the we actually want to keep it there. Because like the thing is Jupyter Notebook remembers this. So when we run output equals output 0 and we do it twice, then we like script indexing. So let's just keep it like that. and just put like the 0th index in here to reduce the dimensions from 2 to 1. And then let's look at this confidence. And is this 76% that we solved before? And this is how we get the direction and confidence of our prediction. Okay, so you can see here, we also have the option to have Python notebooks here. And so what I've basically done is took everything we had and just put it in here. All the input statement. And like the number of time steps, as we remember before, it was declared to be 15. See here, it can be 15. And I've made this into an optional keyword argument, 15, so that if we wanted to use 5 time steps to predict the future prices, we can do that. And all we'd have to do is when we create a temporal CNN object, my temporal CNN, we could just specify a different number, like 25, and that'd be easy. This makes our machine learning model very flexible. So so here we have the create model. Basically, that just builds. Remember before we had the build model and build and create our synonyms. So just called it create model here. It doesn't really matter, honestly. So have the same code. Oh yeah, this is a random note about Python. To make it a function or a variable like private, like in Java, you do like private, blah, blah, private like int, my int or something like that. In Python, instead of using private key, instead of using what do you call it? Private? Like descriptions, variable descriptors, like private, public, stuff like that. Access modifiers. Yeah, instead of using access modifiers to make stuff like private, we can just use double underscore. So because this create model is just a helper model for when we initialize our temporal. The reason it's called temporal is because, as you remember here, temporal is relating to time. If you remember here, we split it into 3 time regions, and time is a synonym for temporal, and that's why it's called my temporal CNN. CNN stands for convolutional network. And we use convolutional layers here, here, and here. So that's why I called it my temporal CNN. The real model, the model that I took this from, the research paper I took it from, it was initially called temporal bag of features. Oh, it's some crazy thing. I can find it real quick. Temporal logistic neural bag of features for time series forecasting leveraging limit order book data. And the thing is, instead of using limit order book data, what I've actually done is use OHLCV data. And this is because book data is quite expensive. So we only have this is usually for like high frequency traders, like market makers who want to use like very good quality book data that has a lot of information. So instead of using book data, we decided to use OHLCV. Okay, so prepare data basically looks very similar. It's just the prep data function that we saw before. Train. So we do not actually, so train basically takes in data from an from a different source. Takes data from a different source. and fits it to, and then we prepare the data using our helper function, and then we fit our model to it. Then our predict basically does, like, if you remember before, we had a scalar, and so so the thing here, fit transform fits fits our data so that it is on a normally distributed scale according to the data, to that data specifically. So every time we input, we have to scale it again. And we have to fill now sometimes. So because data isn't always perfect, sometimes we get not a number values. So we just fill those with, we just fill that like with the past data, like past previous time set data, and we just keep feeding it forward. That's why it's called ffill, because it's forward fill. And then we do the dot values to get the NumPy array from it. Then we pass that data into our model, that we've created. We establish the model here, self.model here. And then we predict, and then if you remember before, we get like a 3x1 array. Well, of 3 values, and we just do what we did before to get the direction and confidence in our notebook, and then we return this direction and confidence. And so how do we turn this into trading signals? Let's go into our main. So QC algorithm basically is an object used by Quant Connect when we run our algorithms to the QC algorithm stores our buy-sell signals and other whatnot. Okay, AlphaStream's brokerage model. You probably don't. Okay. These things are part of a thing called algorithmic framework. They're like pluggable components of a trading algorithm. So brokerage model, this is like a special brokerage model. Like, just think of it as like Interactive Brokers or Robinhood. These are all brokers. Well, Robinhood is not actually supported, but it doesn't really matter. Okay, whatever. Okay, so immediate execution model. So immediate execution model basically means that when we buy something, when we buy a stock, when we order a stock from the stock exchange or like Bitcoin, we do, there's different ways to buy it. Some will like buy it over a period of 1 hour. Some will buy it based on the volume weighted average price. So when it reaches like a good price, it executes a like buy sell orders if the price seems good at the time. However, we decided to go with the immediate execution model. What that basically does is it buys it immediately. So if we send in an order, it automatically tries to fill that order instead of like doing it slowly over time. Equal weighted portfolio construction. What that does is it basically, so say we buy like Apple, Microsoft, and Facebook. What that does is it gives equal weighting to each one. So if we have $900, we would put $300 into each of the tickers. Okay. So add equity basically gives us the stocks that we want to follow. Okay, so on the other page, I use crypto, but since we're only using time series data, I switched to stocks here. The crypto was not working the best in here, so it doesn't really matter because stock data also has open, high, low, close volume values, so it won't change anything. We do it on a minute resolution models. So for each ticker, we want to store a machine learning. We want to store the neural network. And the thing is, because different stocks act differently, and that is why we create a separate model for each ticker. And so this dictionary, we add like, we put like the symbol as key and the value for that key is the model associated with the model associated to the certain trigger window. What this does is it stores our training and prediction data, and we'll use 500 time steps of OHLC data and set warmup. That'll basically allow us to. So what this does is, since we have a start date of June 1st, right? So what this does is it goes back 500 bars of data, in this case 500 minutes, because we specify minutes here. We go 500 minutes into the past, and then it feeds it in, and it feeds it in so that our on data can do any preparations. And this Boolean called is warming up to know if we're in the warm up stage. Okay, so here, self.time is a field that is a datetime object, and so we can access the minute. And so the reason we make it so that we only trade every 30 minutes is to reduce the number of trades, to make sure like the back testing isn't overloaded with too many trades. Trade model, basically what it does is it does some data conversion, and feeds data here. So it establishes a main temporal CNN object, which stores our models and stuff like that. And then we feed in the data. And remember before, this is where the, if you remember before, we had like loc for ETH, so that we only get ETH data. And if we over iterate through the stocks we have, we can access, for each model, we can access only the data we want for that, only the data pertaining to that symbol with this loc. Oh yeah, self.debug is basically what we consider print, but since print is not supported, we use self.debug to like put stuff to the console instead. Trade. So here, what this basically does is it calculates the prediction and confidence here. So it gets the prediction and confidence. And sometimes neural networks can give us not a number value because of like something called exploding gradient. And so we want to make sure that our confidence is an actual number, because that means our neural network predicted something real. And we want to be slightly more than sure. So we want it to be 55% sure, a few percentage above 50%, because we want our model to be confident. And so if the direction is up, then, so insights, basically what they do is it buys the stock now or over a period of time based on our execution model that we've defined. But since we have an immediate execution model, what it does is it buys it, and then after a time delta basically specifies a difference in time. So after a time delta, it sells it. Or if you're going reverse, if you sell it, if you short the stock, after the time delta, it covers the short and we buy the stock. And so what I've done here is time delta. And since we are predicting 1 to 5 time steps ahead, the movement of that, instead of like doing a bunch of insights, I've just did a random value within that, within one of the 5 values of that average. Because if you think about it, if you do a bunch of these trades, it sort of simulates the average, sort of. The reason I do that, I could have an insight for like minutes equals 1, minutes equals 2, minutes equals 3, minutes equals 4, minutes equals 5. And that would sort of simulate betting on the average going up, because we take 5 positions and we hope the average of these 5 positions will go up. However, that would create a bunch of insights and make the back test super slow. And that is why I only do one of those 5 values. And and I randomly determine it so that there is no any sort of bias or anything like that. And then once we've collected all these insights, we emit these insights. So how does this algorithm do? It takes a long time to run, so let's just see how it does. So it starts with $100,000 and goes to 90K in about a month, well, around 3 weeks. So what do we know? Machine learning models may not be the best thing to predict stock prices because it could because there's a multitude of problems like overfitting, detecting basically mining for patterns that don't actually exist. Another problem is because that we eat a bunch of spreads because it trades a lot. If you know about bid-ask spreads, when you hit bid and then you hit ask, or if you hit the ask and then you hit the bid, it comes out of your profits. And because we do it on a minute resolution, we trade on a minute resolution, the spreads might hit our profits. So these are just some things to consider. When trying to predict stock prices using machine learning. However, I just wanted to put it out there on how you can actually do it, even if it is not profitable, because you can continue off this model and develop it and address some machine learning problems like overfitting and such, and make a lot of adjustments like how much data you use, how much the time scale you on, instead of using data on a minute resolution, use daily or hourly resolution. You make all these changes in an attempt to try to find some real patterns and make some predictions that are reliable. So please do not count on this on being a profitable trading algorithm. This is just a baseline for you guys to create your own models. And I hope this has been helpful. If you have any questions, please post it in our Facebook page, message in Slack, or if you know my email, you can email me. If you don't know my email, you can also DM me on Facebook at SchillerWen. And you can also post in the comments on this video if this video comes out. I hope everyone has a good day. Bye.